Okay, so I'll work through this isothermal stirred tank reactor in this example problem that was from a practice exam in process control and dynamics. We have an isothermal, let me just go down to the picture. We have this, this stirred tank reactor here that has two inlets, CA in and CB in, so just pure A and pure B coming in with flow rate Q1 and Q2. And then we have Q out, which is a summation of those two that are coming out. Okay, so there's a reaction that occurs here. It's a well-mixed tank, and then you have CA, B, and C coming out. So C is formed, and let me scroll back up. So we have an A plus B goes to C reaction, and here's a reaction rate for A and for B, in fact. A couple assumptions here are that V, Q1, Q2, and Q out are constant. And the first objective is to derive a dynamic mole balance for A and B. Okay, so let's go ahead and first of all go through this, the steps of deriving a first principles model are first of all to draw a diagram. Now in this case, it's been drawn for you down here. So let's just go ahead and use this diagram and go ahead and write some of our assumptions. Okay, so our assumptions that we have for this are that first of all we know that it's isothermal. We're not going to be doing an energy balance on this, in fact. So and the reaction rate is not dependent on temperature either. Okay, so we also have an irreversible reaction that is A plus B goes to C. Okay, so that's one of the another one of the assumptions. Now let's go ahead and write out our constants again, just to be clear. We have, I'll just circle those, Q1, Q2, and Q out. We also had V as well. And then also, we didn't mention this in the problem, but let's go ahead and assume that K1 from our reaction rate expression is also going to be constant. Okay, so let's go ahead and select which ones are going to be variables, the ones that we're going to allow to change. Okay, so for these, I'll go ahead and highlight these in blue with a square. We have CA in, CB in, and then these three, the reaction rates, or the reaction concentrations coming out of the reactor as well. Okay, so those are our variables for this problem. Okay, so we have a schematic. We've written our assumptions. Let's go ahead and start with our okay, I'm going to scroll up just a little bit. We'll go ahead and start with our mole balance. Balance for A. Okay, so to start off, I'm just going to write the generic mole balance, which is just A in minus n dot A out plus n dot A generation minus n dot A consumption. Okay, so in minus out plus generation minus consumption. Okay, and now let's go ahead and okay, we're going to take this and then go ahead and start filling in some of our terms here. We know that we want this in terms of concentration. Okay, so we have our concentration times volume. Now this is going to be constant. Okay, so when we plug this in here, the volume can just come out front. Okay, so let's go ahead and do that now. Volume d concentration d time is going to equal, then the A coming in is just going to be the Q1 and then times CA in. Okay, and then the concentration leaving is just the Q out. Okay, that's going to be Q out times the concentration within the tank. Okay, so it's well mixed. So the concentration out is the same as the concentration inside this tank. And then we have generation. There's no generation that's occurring. It's an irreversible reaction for consumption of A, but we do have a reaction rate of consumption. This is actually going to be negative and then minus reaction rate times volume. Okay, so if you remember from above, the reaction rate is defined as negative K1 CA CB. Okay, so we'll go ahead and plug that in here for reaction rate. and the expression here, after we cancel these two out, it's going to end up being negative for this term, which it makes sense because it's consuming, and so the concentration is going to, the derivative is going to be negative if that's the only thing that's driving the changes in concentration. Okay, so now I'm going to switch over. I'll just switch over to OneNote now. Okay, and let me go to teaching. I'll go ahead and add a new page. Okay, so now that I've switched over to, I'll switch over here and let me go ahead and continue this. But what I want to do now is I'll go ahead and write out my expression. Okay, so it's dCA dt equals Q1. Okay, now that is times CA in minus, and then that is going to be Q out times CA minus, and then I have K1. Okay, let me make this a little bit bigger. I have CA CB times volume. Okay, so now I'm going to go ahead and circle what are, go ahead and put a circle around all of my constants. Okay, so there's a constant, there's a constant, there's a constant, and there's a constant, and there's a constant as well. The rest of them are going to be variables. Okay, so now I want to also do this for B as well. Now very similar for B, dCB dt equals, and then this is going to be Q2 CB in, okay, minus Q out CB minus K1 CA CB times V. Okay, so this is my mole balance for A, and that's my mole balance for B. Okay, so now what I want to do is go ahead and linearize. I'll start with this expression right here. Okay, the mole balance for A, and this is for part, this was for part A, okay, of the problem, and now I'm going to go down to part B of the problem, which was go ahead and linearize this expression, and then we're going to get into deviation variable form. Okay, so when linearizing, if you remember linearization of a function of multiple variables, what you do is you go ahead and plug in the nominal conditions, okay, and then you go add df dx, plugging in the nominal conditions, so x bar, y bar, z bar, okay, times x minus x bar plus, and then you just do that for all of your variables as well. Okay, so I'm going to go ahead and do that for all of my variables, plugging in x bar, y bar, z bar. Very important that these just become, these are just going to be constants. Okay, constant values after you've taken the derivative and plugged in the nominal values, and then you can do that for z or more variables as well. So what I'm going to do is go ahead and linearize the right hand side of this expression. Okay, that's going to become my f of all these different variables, and then I'm going to plug in steady state conditions. Okay, so let's go ahead and do that. I have v dCA dt. I don't need to change that on the left hand side. I'm just going to linearize the right hand side. Let me go ahead and do it with CA in first. Okay, so the derivative of this expression with respect to CA in is just going to be Q1. Okay, and that's already a steady state condition. Okay, so now I just multiply by CA in minus CA in nominal condition. Okay, and you're probably asking yourself, why did I skip directly to this first one where I take the derivative and multiply by its deviation variable? What happened to this one right here? And if I say that these are all steady state conditions, then that means that this is equal to 0. Okay, so if I plug in the steady state conditions here, if I put the bar over each of these like that, and this equals 0, then this term right here becomes 0, so I don't need to do anything with it. Okay, so I'm going to go ahead and just erase those bars up top here. Okay, so those are, let me go ahead and erase those. Okay, so let me continue on then. So I have CAN minus CAN bar, and then let me go ahead and do this with respect to CBN. Okay, and that's 0. There's no CB there in the equation. Minus CB in bar. Okay, so that's going to go away. Okay, so let me go ahead and scroll down just a little bit, and let's do this now with respect to CA. Okay, so I have plus, and I'll take the derivative with respect to CA. I have minus Q out, and then it's also going to be minus K1 CB times V. Okay, and then that's going to be CA minus CA in bar. Okay, now this term right here, you're saying, whoa, there's a variable right there. Well, it's really not. It's just at the nominal conditions. So this is going to become a constant. And I'm going to rename that alpha. Okay, and then I also have my next one with respect to CB. I scroll back up there. The only CB that exists is in the reaction expression. Okay, so that's going to be negative K1 times CA bar times V, and that's CB minus CB bar. Okay, and why did I put an in there? I shouldn't have put it in there. Okay, so now I have my linearized expression. I'm going to also call this one beta. Okay, so I have alpha and beta. So let me go ahead and write out my linearized expression for A. Okay, now I have Q1, and then it is going to be this is defined as a what's called a deviation variable now. Okay, so I have CA in is equal to CA in minus CA in with the bar over the top. That's called a deviation variable. So the initial conditions for this are equal to 0. Okay, that's going to be equal to 0 there. And so I'm just going to write this in terms of deviation variables. Put the prime there. Okay, and then I have plus alpha times CA prime. Now this is a function of time, and then plus beta times CB prime. Now you see this is CA right here. We want to get that into CA prime. Okay, so let me just go ahead and write out the definition here. CA prime equals CA minus CA bar. Okay, and then I just differentiate both sides, and I see that I have CA minus CA bar dt. That's a constant, so that's going to go to 0, and then I have dCA dt. Okay, so I can plug in this expression right here, just add the prime. Okay, so now I have the expression for the linearized expression in deviation variable form for A. So let's go ahead and do that for B as well. I have my, okay, so this is my mole balance for B. Let me go ahead and do the linearization for this one as well. Just have to remember that one as I scroll down. Okay, so I think I've got it. Let me go ahead and just write it out here just in case we forget some of that. dCB dt equals, and then this is going to be Q2 CB in, and then we have minus Q out CB, and then we have minus K1 CA CB times V. Okay, so let's go ahead and do the same linearization that we did just like for A. Okay, so we take V dCB dt equals, okay, take the derivative with respect to CA in, and that's 0. CA in minus CA in bar. Okay, so that term goes to 0. Then I have plus Q2 CB in minus CB in bar. Okay, and then let's do it with respect to CB, and then plus, and then I have negative Q out minus K1. Let's do it with respect to, yeah, I should have done, let me do A first. I went out of sequence. Okay, so this one should be plus negative K1 times CB bar times V CA minus CA bar. Okay, and then let me do it for B as well, and that's going to be negative Q out minus K1 CA bar V times CB minus CB bar. Okay, so there I've got my linearized expression. I'm just going to rename some of these. I don't want to be able to have to carry around a lot of constants, and so I'm just going to name this as gamma, and I'll rename this as delta. Okay, so now I have a linearized expression for CB. So CB dt equals, and then it's Q2 times CB in prime plus gamma times CA prime plus delta times CB prime. Okay, there I have my next one that is linearized. This is CB. Now what we want to do is go ahead and get this one into the Laplace domain. Oh, and I forgot this one, same rules before. You just add the prime because you differentiate both sides of the definition for CB prime. Okay, CB. Okay, and differentiate both sides, and that equals this, and that's why we can substitute in and just put the prime there. Okay, so now what we want to do is go ahead and take this into the Laplace domain, and the instructions for this problem kind of step you through this. All of the steps that you need to be able to combine B with A. So let's go ahead and solve for CB first as a function of CA. We're just going to assume in this case that CBN is constant. Okay, so the deviation variable does not change, and we're going to do V times S times CB of S. I guess you can look this up in the Laplace tables. And you know that when you take a derivative with respect to time in the Laplace domain, you multiply by S, and then you subtract the initial condition in the time domain. But because this is a deviation variable, that initial condition is 0. And you'll see also that you could carry around the prime there. We already know in the Laplace domain that these are already in deviation variable form, so you don't need the prime. Okay, so I'm going to write the rest of it. I have gamma times CA of S plus delta times CB of S. Okay, now let me just go ahead and combine terms, and so that is V times S minus delta times CB of S equals gamma CA of S, or in other words, CB equals gamma over VS minus delta times CA. I'll put the S there just to make sure remind us that we're in the Laplace domain. Okay, so now we have CB relationship to CA. Okay, I'm going to do the same thing with bringing this expression into the Laplace domain, and then we'll combine the two expressions and see if we can get an overall expression for how CA, how that's going to change with an input change in CAI. Okay, so CB in is not going to change, but CA in is going to change. Okay, so let's go ahead and take this one down below. Okay, so I have, let me just go and write this out. V d CA prime dt equals, and then that is going to be Q1 times CA in plus alpha times CA plus beta times CB. Okay, so let me see if I got that right. Okay, and I've got to put the primes back on that as well because we linearized it. Okay, so let me bring this one, I'm going to bring this one into the Laplace domain. So that is V times S times CAS equals, and that's Q1 CAN of S plus alpha CA of S plus beta times CB of S. Okay, so now I have this CB of S that's going to come from there. I can also go ahead and collect the CA over onto this side. Okay, so let me go ahead and do that. VS minus alpha times CA of S equals Q1 CAN S plus beta times gamma divided by VS minus delta times CA of S. And of course I want to collect the CA onto this side as well, but let me go ahead and do that, and then I'll divide over. Okay, so give myself a little bit more room here. Okay, so that's going to be VS minus alpha. You know, maybe it'd be easier if I just multiplied through from the start. Okay, so let me multiply both sides through by this VS minus delta. Okay, so VS minus delta times CA of S equals Q1 times VS minus delta times CA in of S plus beta gamma CA of S. Okay, so I'll go ahead and subtract that over and then divide it through to get my transfer function between CAN and CA. Okay, so let me just do this quickly. Minus delta CA of S. Okay, and subtract that over, minus beta gamma, okay, times CA of S equals Q1 VS minus delta CA in of S. Okay, and then go ahead and divide through. CAN of S equals this Q1 VS minus delta divided by VS minus alpha, VS minus delta, minus beta gamma. Okay, so I have my overall expression, my transfer function between CA and CAN. And so what type of system is this? If I multiply it out, I'll see that I have an S squared on this term. So it's going to be a second order system for this transfer function. Okay, so depending on the constants that I have, it could be an underdamped, overdamped, or critically damped system. I also see that I have a 0 up here as well, so that I could create some overshoot or inverse response depending on what I have for the constants and reaction rate expressions. Okay, so that concludes this problem. Let me just go back to see if we were able to answer everything from this problem. Okay, so let me just review the steps that we took. We derived the dynamic mole balance for A and B. We linearized the equations. We put them into deviation variable form, so if you remember the prime right there, then we put it into Laplace coordinates, okay, and then we solved for CB. Okay, you can generally just leave off that prime right there. Then we substituted this into the appropriate place in the mole balance for A, okay, to get rid of the CB of S. Okay, so that was no longer existing, it was just CA of S and CA in of S. Okay, we're trying to get a transfer function between those two. Okay, and then what order is the transfer function? You look at the polynomial degree on in the denominator, and then we saw that that was going to be an s squared, so it's a second order system. Okay, so that concludes this problem for this reactor and how we've modeled it, the first principles for a species balance, and then created the transfer function for how the concentration outlet changes with concentration inlet.